Albedo represents the reflectivity of a surface. How much radiation is returned from the surface compared to how much radiation strikes it initially. By default, then, we can determine, or we can infer, how much heat radiation is absorbed into that surface. Look with me in pages 44 and 45 of your Essentials of Meteorology text. Starting with Table 2.2, reflectivity varies with different surfaces. And this can make sense as you think about it. A snow-covered field reflects a lot of radiation, 75 to 95%, maintaining the cool. Sand, on the other hand, absorbs a lot of the radiation, heating it up, if you think about hot bare feet on the seashore in summertime. Still on page 45 of your text, figure 2.17 gives an overview of the radiation energy sent by the sun. For every 100 units of solar radiation that hits the top of the atmosphere, 30% of that is reflected and scattered by different things, reflected from the Earth's surface, from the clouds, or from the atmosphere, and 19% of that is absorbed by the atmosphere and clouds. This leaves 51% of the sun's solar radiation to be absorbed by the Earth's surface. The interesting thing is that something has to happen with that 51% of solar radiation to keep the Earth's surface in equilibrium, or the same average temperature. If that 51% is not dissipated in some way, the surface of the Earth would continually get hotter. This is illustrated in figure 2.18 on page 45 of your text. If 51 units of solar heat is absorbed by the Earth's surface, 51 units of solar heat must be released from the Earth's surface. How is this done? Of the 51 units absorbed at the Earth's surface, a large part, 23 units, is used to evaporate water. Remember our discussion on latent heat of H2O in the atmosphere? Evaporation of water removes latent heat from the environment around it. Figure 2.3 in your text. In this case, the Earth's surface helping to balance out the solar radiation. Those 23 units of solar heat that are lost from the Earth's surface are gained by the atmosphere. Continuing on, of the 51 units of solar radiation absorbed at the Earth's surface, convection and conduction account for the loss of about 7 units. Conduction, the flow of energy or of heat energy from warmer to cooler regions, and convection, vertical exchange of heat. That is, warm air rises and cools as cooler air falls and warms. Those are discussed on pages 33 and 34 of your text. But it's responsible for the loss of about 7 units of the solar heat energy, which is also then gained by the atmosphere. The remaining 21 units of solar heat are radiated away as infrared heat. But wait, the figure shows 117 units are radiated away from the surface. The Earth radiates infrared heat all the time, day and night, not just when the sun is hitting it. Notice that only about 6 units of the infrared heat from the Earth's surface make it to space, while the remaining 111 units are absorbed into the atmosphere and then radiated back to Earth. Remember in our previous slide that 19 units approximately of solar radiation was absorbed directly by the atmosphere as the sun's rays passed through it. So now if you add up all of the energy gained by the atmosphere, you'll come up with 160 units. Of those 160 units, 96 are gained back to the Earth's atmosphere, while 64 are lost back to space. Notice just 2 more things here. First, the amount of energy gain at the Earth's surface is almost double that through infrared radiation absorbed from the atmosphere than from the direct solar radiation from the sun. And second, there's a delicate balance that's maintained between, or as the Earth and the atmosphere absorb energy from the sun as well as from each other to maintain that delicate balance.